Hello everyone, welcome back to another lesson in Algebra 2. This is our sixth lesson and our second unit. We've been studying linear equations for the past few lessons, and we're going to finish off that discussion by talking about linear regressions and lines of best fit. Linear regression is an extremely important tool in science, social science, and mathematics. It is used to make conclusions and uh, observations about all sorts of things. For example, the idea that smoking causes lung cancer or that running is good for your health. Things like that are all based on linear regressions. They are also things like population predictions, polling, all sorts of things use linear regressions. So let's fill this in together. The line of best fit. The line of best fit is a line found using the least squares regression method that best approximates a set of data with a linear association. The correlation between two variables, let's fill that in. The correlation between two variables, that's a correlation. The correlation is the tendency of a change in one variable to correspond to a change in another variable. There are other ways to find a line of best fit than the least squared regression, but the least squared regression technique is by far the most popular and accepted method. The Pearson's correlation coefficient, oftentimes just called R, describes the strength and direction of a linear relationship between two variables. R is bounded between -1 and 1, where R equaling -1 represents a perfectly negative correlation, a perfectly linear set of data that is going down, and R equals 1 is a perfectly positive correlation, meaning that all the data fit perfectly in a line that's going up. The least squared regression method finds line with the smallest sum of areas of the squares of all the errors. One thing is really important. The most important part of linear regression is the R value. It tells you how confident you can be that a change in one variable will result in a change in the other and which direction that change will be. For example, the idea that a change in the number of cigarettes someone smokes every day is a change in the likelihood that they'll die young from lung cancer. That's a bad but positive correlation. And that's what the R tells you. However, the R value does not tell you how much. For example, perhaps a certain fertilizer that you feed into a flower will correlate with larger blooms. The R tells you how likely increasing fertilizer will increase the size of the blooms. It does not tell you how much it will increase them by. Let's take a look at this kind of a pictorial representation of a least squared regression. The process of finding a least squared regression is outside of the scope of this class, although I hope you get to see that. It's relatively straightforward. It's just time consuming. But for our purposes, a pictorial understanding should suffice. So when you have a set of data, in real life, data are messy. They rarely, if ever, fit on a line. So when we find the line of best fit, we're not trying to actually go through any of those points. As you can see, my blue line does not go through any of these red points. It may go through some, but we're certainly not expecting it to. Our purpose is to draw vertical lines from each data point back to our line of best fit, and then construct the square of that, which is represented by these green squares. And what we're trying to do is find a line that when you add up all of these areas here, all the area of these green squares, that area is as small as possible. So you can imagine us playing with this line and adjusting its starting y-intercept and its slope to where those, as I move it more up, it would, maybe the squares below it would become bigger, but the squares above it would become smaller. We're trying to find that perfect happy medium where all the squares are as small as possible. One disadvantage of this particular technique is that since we are squaring those errors, what we call outliers, a point way off to the side, oftentimes has a tremendous impact on the correlation. What is extremely important, and you can fill this in the bottom of your notes, is that correlation does not prove causation. That is one of the things that everyone must learn before they start studying statistics. If A causes B, there will be a correlation. And so finding a correlation is a good excuse for us to conduct an experiment, a controlled blind experiment. However, certainly just because A correlates with B doesn't mean it causes that correlation at all. One of the most, common correlations might be to say that people that ride bicycles will one of the most common correlations that is mentioned is something like a student going to a private school is correlated with a high score on their SAT. As a public school teacher, and a very proud one at that, I find that correlation to be not at all convincing. Of course, private schools would have students with high SATs, because if they are going to a private school and spending all that money, they're probably also studying for their test. Whereas at public school, we have all sorts of a variety of students. Students that study a lot and students that don't. And so it's perfectly normal to expect that. That's a correlation. It doesn't prove causation. It doesn't mean that going to a private school will make you score better on some test. It just means that if you go to a private school, you probably study. Right? We could continue on and on with other correlations that they don't necessarily prove causation. Some of them could be even sillier. For example, the number of seashells in a county corresponds to shark attacks. Does that mean that seashells cause shark attacks? Well, no, obviously not. It's just that if your county has a lot of seashells, you're probably on the ocean, and the ocean is where shark attacks occur. We could go on and on with silly correlations like that. So it's important to remember correlation does not prove causation, but it is a good first step in identifying things. So, for example, when we saw that there was a correlation between smoking and early death from lung cancer, an experiment was conducted, mainly a social experiment, where they traced people's lives and they investigated medically and they did all sorts of things to try and figure out what is going on. And sure enough, they were able to prove causation between the two. Okay, let's take a look at an example. Let me just clear all this out first. All right, I have values of acceleration due to gravity and in centimeters per second squared, and the escape velocity in kilometers per second for 4 of Jupiter's moons as shown in the table below. What I'd like to find is the correlation coefficient for this data. So we would expect a very strong correlation because the escape velocity is almost exactly tied to the gravity. So let's go ahead and find out what that would be. We can then use that correlation and least squared regression to make some predictions. So I'll be using the Desmos graphing calculator today. And what we're going to do is you need to add an item right here. And we're going to select table. And I'll simply type in these data right here. One thing to remember about data is data are plural. So every time I speak, I have a bad habit. You'll catch me trying to avoiding it, but you should always refer to data in the plural. So you don't say I'm going to enter this data, I'm going to enter these data. But as you may have noticed, I have to catch myself because it's a difficult habit to break. All right, so we have some data here. We can certainly graph the data, and they even have a nice little zoom fit feature. Oh, you know what? That's probably... Oh, no, that's not the one. What is that one? What is that point? I probably am... I did. I put a 0 in the wrong place. That's why we always graph our data first, right? Okay. So there's the data. You can see it. It definitely appears to have a stark linear relationship between the gravity and the escape velocity. And so I'll do y tilde. Tilde is right above the tab key on mine. And then I'll say mx plus b. x1 plus b. Oh, do I not put the 1 there? All right, now we need to get the linear regression. The way that's done is pretty much every calculator can do it, even simple scientific. Definitely all graphing calculators can. You put y sub 1, or whatever it is that you labeled this entry here. Ours is just y sub 1. And then you hit the tilde, which means approximate. And so it's right above the left tab key on my keyboard, just to the left of the 1. I have to hit shift. Then we'll put m for slope, and then we'll say x sub 1 for x sub 1. And then we'll say plus b. And that should give us the statistics that we need, the slope of our equation, and the y-intercept. And you'll notice that it goes very closely through each one of those points. That's because it's pretty much a direct calculation between the escape velocity and gravity. Look at our R value. Our R value is 0.9999. The R squared is exactly what it sounds like. It's the R value squared. That's important for other things, not for what we're doing today. So we're going to say the correlation coefficient for these data are 0.999. That means that these data are in a pretty much perfect linear relationship. I would argue the only reason why it's not a 1.0 exactly is simply rounding. So that is a very strong relationship. But now that we have that model, we can use it to make predictions. So I will simply type it in, x plus negative 0.04. Okay, so now that we have that model, we can, I'm actually going to call it this. I'm going to say f of x. We'll use function notation. We can predict the escape velocity on the moon Pan, whose gravity is 1.0 centimeters per second squared. That's an x value. And so you can see that the escape velocity is 0.0154 kilometers per second. So our R, let me just help you fill in these notes right quick in case you missed that, was 0.999. What does that mean? This is a almost perfect positive correlation. And the model that we used was y equals, help me out if you remember, 0.0154. I forgot the 5. X minus 0.000. I think it was like a 4 at the end there. Basically, it's a 0, right? Okay, so then we calculated y of 1.00, and the value that we arrived at was 0.0154. Kilometers per second is the escape velocity necessary to escape that moon of Pan. All right, let's take a look at another chart. Okay, so I've got a chart below that describes the orbital radius and orbital velocity of several moons of Jupiter. I'd like you to describe the manner of correlation between the radius and the velocity of the moon's orbit. So, I don't know. Do you think this is going to have another super strong correlation? Maybe. Looks like one of my numbers here of Callisto fell down. So this is a 700. Probably need to reformat that table, I guess. Anyway, I want you to put it in there. I want you to see what kind of correlation there is between the radius and the velocity of the moon's orbit. So pause the video and give it a try. Okay, let's see how you did. I'm going to go ahead and just start from scratch here so I can enter a table. We'll just go through the whole process again, okay? So again, we can label these things different values, but I'll just use x1 and y1. I've got 128,000, 129,000, 181,400, 221,900, 421,800, 671 with a few zeros, 1070400. 1070400, 1882700 and 7507000. Well, boy, the misto. Far out, huh? 31554, 31480, 26489, 23905, 17340, 13743. I think I mistyped that. There it is. Then we should be on Ganymede, which is 10879, 8203, 4136. Okay, so it definitely felt negative, didn't it? Click on this little button here. It should zoom out. Ooh, that is an interesting shape. Not exactly a line, but definitely a shape, don't you think? Let's get the regression here. So I'll just say y sub 1 tilde m x sub 1 plus b. Okay, so not exactly a tight linear formation here, but definitely a negative correlation. Negative correlation, the R value is about negative 0.7. That, scientifically speaking, that's a very strong correlation. Now, you can look at this and say, yeah, but it's not in a really tight line. Yeah, but the confidence that we have now that an increase in the orbital radius will result in a decrease, excuse me, because it's negative, a decrease in orbital velocity is very strong. 0.7 is still considered a very strong correlation. And as you can see, perhaps a linear model would not be the best and most accurate way of predicting it, but that R still is very powerful in describing that this is a somewhat strong negative correlation, and we certainly feel very confident that that's exactly the relationship that's happening. Okay, good. All right, so you have some more practice problems. I want you to calculate the line of best fit just for some generic data. Sorry they don't have a cool, like, interstellar word problem, but go ahead and do that for practice 6.2. Pause the video and give it a shot if you don't have your notes in front of you. There it is. All right, let's go over it and let's see how we did. All right, I'm going to make a table. I keep starting from scratch here because I really want you to feel comfortable with this procedure. And then I'll type in my y's. 5, 20, 15, 12, 31. And I'll do a nice little zoom fit. Ooh, pretty scattery, huh? Y sub 1 is approximately mx sub 1 plus b. Well, it is a positive correlation. 0.2448 is the value that you would put down for your answer. That's not a real strong one. Really in statistics, we kind of need to see like a 0.3. I would be hesitant to state that with much confidence that increasing X would result in an increasing Y. It's just not that strong. So that's a weak positive correlation. All right, let's take a look at our next problem. And I'll bring it over here on this board. All right, a patient starts to take an antibiotic. After the first day, the germs in the blood count totaled 3,052. On succeeding days, the germ count was 2,400, 2,150, 1,500, 1,300. Based on a linear regression, how many total days should the patient take the medicine to kill off all the germs? And how strong of a correlation is this? Okay, give that a shot. All right, we're going to be entering these data. So there we go. I'm going to be entering these data into a table. So on the first day, I'm going to call that day 1. That's kind of the tricky part of this problem, right? Because it seems like they only gave you one piece of information, but they're telling you the successive days. So you know that that's what's going to be our X and Y. As far as I know, you could actually put them in. You could put the days for the Y and the germs for the X, and we should get the same answer. So that should not make a difference. But it seems to me more logical that the amount of germs depends on the number of days you've been taking the antibiotic. So that definitely seems to be All right, we have a negative that we expect, not a perfect line, but that is really a pretty tight correlation. I'm expecting a pretty strong R value here, probably in the nines. M x sub 1, well, then it'll be a negative 0.9. Remember, the R value will be negative if it's a negative correlation, positive is positive, close to 1 or negative 1. Yeah, negative 0.98. That at 5. That's a very strong correlation. We could actually use Desmos now to just, it says how many days. I would take it. So that's the 7th day of taking medicine, sometime during that 7th day. So I guess I would take it at least 7 days, maybe 8, but probably 7 would be enough. I don't know enough medicine to tell you what to do there. So 7.724 is the value of days that would eliminate the germs. So I would say either 7 or 8, depending on whether or not, because I'm thinking you take it on the 7th day and it's going to work all day. So that probably is enough. Okay, so next, I think we have. Oh yes, this is an interesting problem. Okay, so this is I don't know why this problem is kind of famous, but this is the fires and thefts per 100 people in randomly selected zip codes in Chicago. We're going to approximate a linear model for the following data, then graph the data and your model, and use a calculator to determine the best fit line. State the correlation coefficient R and describe its meaning. Finally, discuss limitations to your model, particularly whether it represents a cause and effect situation. Okay, so what I'm going to do is let's just go ahead and do this one together, because I want you to do something a little different. I want you to experiment with trying to calculate, not exactly calculate, but just kind of guesstimate a line of best fit. Because I don't think we've done that yet. We've just gone straight to the calculator to calculate it for you. And I just want you to see how good you could be at guessing one. All right, I'm going to put the thefts in for Y. So if you do that with me, please. And if you have a printed out copy of the notes, there is a kind of a rinky-dink little graph that you could fill in there if you want to use that. But I'm just going to use this, and let's zoom fit. Okay, why did you not zoom fit? Ah, there it goes. Okay, so what I want you to do is actually come up with your best guess at what it would be. So for example, maybe you think this is 5x minus 20. Or something. I don't know. Or maybe you think it's negative 2x plus 18. I want you to come up with your best guess at what you think this is. Feel free to try several different times until you find the one that's right. Remember, you're trying to minimize the squares of the errors. And then we'll go over it. So press pause and try your best. Okay, so let's see what you get. To me, I look at this, and it definitely looks like it's going up like 6 or so. With the minus 10 maybe for y-intercept. Well, maybe that's too fast. See, well, that's actually still too steep. Maybe 4x, and then actually plus a few. All right, I'm going to go with that. 4x plus 5. What did you go with? So y sub 1 is approximately mx sub 1 plus b. 3.5. Okay, so yeah, I was still too steep, wasn't I? 3.5, and my y-intercept was too low. Now, y-intercept would represent the number of thefts that we would expect in a neighborhood that had 0 fires. Okay, so I'll get rid of my estimate now that I've got that. So let's talk about this. The correlation coefficient is 0.95. That is extremely strong. So there is a very strong correlation between fires and thefts per 100 people in zip codes in Chicago. So do fires cause theft? Perhaps if a community is saddled with a high crime rate, then what we should do is make sure all their buildings are up to code and there's a fire station nearby, right? No, obviously not. So this is one of those ideas of a correlation not proving a causation. What's happening here? There's probably something else at play. And I would guess that in a neighborhood where crime has taken hold, the quality of the buildings will be low. The the living standard, the amount of people per, notice that we're talking about per 100 people. We're not talking about amount of people in the zip code alone. Anytime you have a densely populated area, I think theft is going to be more accessible, more for crime is going to be more easily done. And also fires are going to be more devastating. A small fire in a spread out area, which is less likely to have theft, is going to have less of it, is going to affect less people, whereas a fire in a densely populated area would. This is not this is not saying that fires cause thefts, but what we might be seeing is that communities that are dealing with fire tragedy and the crime of theft have something underlying conditions that need to be addressed, and that if we're going to help a community that is experiencing this plight, that we need to figure out what exactly needs to be done to make that community safe both from fires and thefts, and perhaps there might be some underlying cause that we're not aware of. So that's the kind of approach I want you to take to these kind of regressions. All right, I have just a little practice here. I want you to match the R value to the correct corresponding graph as best you can choose. So take a moment, pause the video, and see if you can identify which one of these R values you would put with each one of these graphs. Okay, this graph here does not appear to have much of a correlation at all. If it did, I would probably think a negative one. So yeah, the negative 0.108 definitely seems reasonable. This is a fairly tight positive graph. It's not a super straight line though. 0.683. Okay, I would have actually thought it would be higher, but that's the only choice that makes sense. Of course, I don't have the units here, so I don't know how spread out that really is. This here is quite a straight negative. So we got two negative correlations that we could choose from left. Definitely the higher of the two here. I mean, all of these are pretty darn tight there, to tell you the truth, but we can still, just using our common sense and comparing the different values, that's a nice exercise. I like that question. Expect to see it on a quiz or a test. Just make sure that you know what R is and what it means. Remember, R does not tell you how strong the change is. Excuse me, it does say how strong the correlation is. It doesn't tell you how much the change is, right? It doesn't tell you the slope of the line. You would need the slope of linear regression. It just tells you how tight a fit it is. But it is the most important value in the linear regression. So yeah, I just close with that. Seems like I'm ending my notes that way. Let's go through it together. It's important. I want to address these misconceptions. The correlation coefficient R tells two things. It tells whether the correlation is positive or negative and how strongly the variables are correlated. But it does not tell you the steepness or the slope of that regression line. And remember, correlation does not prove causation. If you think hard for an exit ticket, I think you can think of some situations where there are very strongly correlated data, but there's certainly not a causal relationship. So that's it for linear regression. We'll start something new next time. Until then, take care.